Hi everyone, today marks the last video in this series on pattern synonyms where we're going to see how pattern synonyms can be used to make a safe interface, or what is safe on the outside interface, in a richly typed program that works much faster than sort of the natural one that you would write. So this is quite a bit of a bigger program than usually we see in these videos. All the code is available on GitHub. There's a link in the description so you can play around with it. But one particular file we're going to build up as we go, and that's sort of going to be the interesting part. So let me show you what this does. Here's main, sort of where the rubber hits the road. And if I run the program, let me build it. Hopefully that works. And in a moment we can run it. And all it does is print out the numbers from 0, whoops, went too far, from 0 down to 99. So let's see how it does this. What it's doing here, well, it's building up a vec of fin. So we'll come back to that and explain exactly what that is. And then we're going to look at some of its performance, which is not so great, and then see how we can make it a little bit better. So I say this is a vec of fin. So we're going to sort of work top down here to explain what this is doing. So this is creating a vector. Here's the vector type. This is a length index vector. If you watch the videos on type level programming, you would have seen a lot of these length index vectors in those videos. And really, this is just at runtime, this is just an ordinary linked list. This is the same as the list type. All that's different is that it tracks its own length. So when we have a vec5a, that has to be exactly 5 elements. And so what we can do with this is we can, or actually before we get to vec of fins, let's talk about vec ends a little bit. So if I know that there's only 5 elements in a vec5a, then when I index into it, I want to index into it with something called a fin. Fin is short for finite set. And this is a number type that is restricted. So a fin5 can only be 0, 1, 2, 3, or 4. It can't be any other number. And our type system verifies this. And so that means that this indexing operation is total. There's no maybe here, and there's no error or undefined or something going on in the definition. I know this is going to be a total function because I know my length of this vec is n, and this index has to be between 0 and n. The type system guarantees that. Then down here, vec of fins, this creates a vector of length n containing all of the fins. Right? So this is going to be this vector that counts 0, 1, 2, 3, 4 if it has length 5. And so I have to pass in an snat n. So an snat n, this is the singleton natural number that represents n here. So if I pass 5 in, then I know at runtime that the number is 5, and I also know at compile time that this n is 5, and so I can build a vector of length 5 that contains fin5, and it will, in practice, contain 0, 1, 2, 3, and 4. The type system does not guarantee that it contains that particular sequence of numbers. It just guarantees that we have 5 numbers and that they're all between 0 and 5. And it turns out that the implementation does 0, 1, 2, 3, and 4 here. So what's interesting here with vec of fins is that I need to pass in this singleton because at runtime, I need to know how many numbers to actually create. And I also need to know this at compile time because my types are tracking the length of my vector and the bound of my fin. Okay, so now we can work our way down one next step to fin. So here's the definition of fin. I don't want to get into the details of how this works other than what I've already described, that if I have a fin5, it can only have the values 0, 1, 2, 3, or 4. As we often do in sort of fancy type level programming, this fin is encoded using unary, which means that when I have, say, a fin value 4, what that really is in memory is a linked list of length 4 that contained no data. And so it's sort of an encoding of its length. This is a really, really, really silly way of storing information, but it's a really nice way for this compile time reasoning. So we're going to come back to this point pretty soon. And then there's some conversion functions because we want to be able to convert fin to int and int to fin and things like that. We'll come back to these functions a little bit more later. We have singleton naturals here. So again, if you've seen singletons, there's not really any surprises here. It's just this normal definition of singletons, again, encoded using unary. So if we have a singleton representing the number 5, that's going to be a linked list of length 5 that contains no data. Very, very silly way of storing information. And then finally, at the bottom of this pile of definitions, we have plain old nat, which is again in unary. Okay, so that's the setup. Now, if we go back to main, we can see what's going on here. So I'm creating a vec of fins of length n. Well, what's n? N is the conversion of 100 to be an SNAT. Because when we convert from an int to an SNAT, this SNAT carries some type level information. And so I need to use continuation passing style. If we look at with SNAT here, we see that it takes in a natural, and then it's going to convert that to an SNAT, but this continuation function here has to work for any number n. That's because we don't know at compile time what it's going to be. So this function has to work for any n. There's not a convenient way of writing with SNAT without using continuation passing style. We could use existentials, but they're not convenient yet. So we're just going to use this continuation passing style. By the way, if at this point in the video you're just being overwhelmed with all these definitions, the upshot of all of this is how pattern synonyms can improve performance. We will see that, but it is pretty type heavy. But maybe you can still sort of glean some of the ideas of that you can. This is an application of pattern synonyms. We'll see it. You're not going to have to build on too much of this knowledge to understand that payoff. Okay, back to main here. So we convert 100 into an SNAT, and that SNAT is going to be called n. And so now, because it's an SNAT, I can build this vec of fins. If I point here, we can remind ourselves of the type of vec of fins. It takes this SNAT n and returns a vec n of fin n. So if we pass in 100, we're going to get 100 different fins, all ranging from 0 to 99. And then I'm going to print them. The one extra step I take here is to call fresh fin. Fresh fin is defined in fin here. It does this. If you look at that, it's the identity operation. It maps f0 to f0 and fsuck to fsuck of the recursive call. The only reason to do this is to destroy sharing, which actually makes our performance worse. But it's needed to see the effects of what's going on. In a real program, sharing does get destroyed. If we build structures that carry data in common, as we perform any kind of pass over those structures, that will destroy sharing. And so this is just sort of mocking that behavior. Mocking up that behavior. It's not making a mockery of it. Okay, so that's what the program does. Now I want to run this, and if I sit pass plus RTS dash S here, then I get the output. If I scroll up enough, we'll see the actual output here. But it also tells me how much information was allocated. So in this case, we allocated just short of a megabyte to be able to produce, to be able to run this program. Now, if we think about this operationally, well, what is this? This vec of fins, that's going to be a linked list of length 100, where each element is itself a fin. So toward the end of this list, we're going to have numbers like 97, 98, 99. Well, 97, 98, 99 are all represented in unary, so that's another linked list. And that means that this structure is actually quadratic in size in n. So we could probably fiddle around with that number 100 and observe the quadratic nature. We're not going to do that. Let's just trust that it's quadratic. Quadratic is bad. But it's really hard to, or at least I don't know, I should say, how to model all of this stuff and keep all of the nice type-safe properties of being able to, for example, index into a vector safely in a total way, without using this unary encoding, because it turns out that the fin, the structure of fin, exactly maps to the structure of vec. And so I can go through one node of the fin for every node of my vec, and this works out really nicely. And yet, unary. So what we're going to explore now is how we can take this safe interface using this unary encoding and instead change it to an unsafe interface, or I shouldn't say unsafe interface, an unsafe implementation of this idea that is not unary. So what I'm going to do is I have finsafe, that's what we've been looking at. Here's finunsafe, which is now empty. You'll see that there's something down at the bottom. It's I got this all working beforehand, and it's all commented out. There's just comments in this file. I'm not going to scroll down and spoil the fun, but it really is just comments. There's nothing else here. And so what I want to do is I want to take the interface that I built up here in finsafe, copy it over, but then make it work without using unary. So the first thing to do, is not that, is to take this, and we're going to copy that over here. I've already run into some trouble here, so I want this to be fin unsafe, not fin safe. Okay, and then there's a lot of complaints because we don't have any of these things yet. So let's do piecewise. Let's get fin first. Well, fin, I said I don't want it to be in unary, but I do want it to have the same type as the other fin. So we're going to say type fin is nat to type. It's still going to be indexed by a nat. So let's have some fun doing, well, we'll have to import data.kind, and we'll need standalone kind signatures. I said we'll need standalone kind signatures, but just because I want it doesn't mean we'll get it. Strange. I bet, aha, it's going down here. Well, let's just kill all of that. Okay, you didn't see that. That was a bug. We add standalone kind signatures. Ah, hooray, good. Now we need to import nat, and so we're going to import natsafe. And then now here, this is probably just complaining that we don't have a binding for it. Okay, fine. So we're going to say data fin n. Wait, no, I don't want this to be data fin n. I don't want this to cost anything. I want this to be a new type fin n, unsafe mcfin, and then, well, it's going to store an int, so I'll just call it fin to int, so I get that function for free. And then this stores an int. Okay, so now what are we complaining about? Now type constructor nat cannot be used here. Oh yes, let's add data kinds. That sounds quite sensible, doesn't it? Okay, so it's green. This is now compiling. Excellent. And we have our fin. We can now create it. It's unsafe. So we're not going to export it with its constructor. We're just going to export fin. But we do get fin to int. We haven't done these other ones yet, so we'll comment that out for now. Now that I've done this, I can go and let's take vecsafe. I've already converted this to vec unsafe, but now I want this to use fin unsafe internally. And so, now we need some of these other conversion functions. Okay, let's implement them. So we need this unsafe int to fin. So I can go over to finsafe and snaffle out unsafe int to fin into fin unsafe. Okay, so this needs snat. Can I import snat safe? Yes, I can. And we'll need, well, this is the old definition, but the new definition, well, I said it's unsafe. We're not going to check it. So let's just call unsafe mcfin of f. There we go. I've completely ignored the index. And I can get away with that because it's unsafe. Okay, so that's good. Oh, now I need to actually export it. So we'll just do that. I think that will work. And now vec unsafe is happy once again. If we go to main, now I also want this to use the unsafe one. Okay, so now we need this fresh fin. So let's go to finsafe here. And we'll copy fresh fin over to fin unsafe. Let's see. So now this old implementation is going to be no good. Fresh fin of unsafe mcfin n equals unsafe mcfin n. That sort of freshens it, although operationally this will do nothing at all, right? Because this constructor doesn't really exist at runtime because it's a new type. And let's export. Okay, and let's see, main is still complaining. Why is main complaining? Couldn't match finsafe.fin with this fin here. And let's see, why is that? That's because someone is importing the wrong thing. So vec of fins is making fin, but this says unsafe. Why is this happening? Oh, haha, I'm importing the wrong one. I want to import vec unsafe. So now we need to print no instance for show fin n. Oh, good, I can do that. Let's go to fin unsafe here. And I can deriving new type show. Because I want show just to behave on this field here. And so we'll add deriving strategies. And what's the complaint here? Can't make a derived instance. Oh, well, I need generalized new type deriving, so let's do that. And, oh dear, that's another problem. Let's just get rid of that. That's not going to slow us down. Okay, so now everything is working. Let's see. Can I build this? Cabal build. Chug, 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 chug. And let's run, and let's see how this performs. Wowee! That's a huge improvement. Although I cheated a bit. I changed vec to vec unsafe, which actually uses real vectors under the hood, not linked lists. So let's not do that. Let's change this instead to be vexsafe. But I'm going to change vecsafe to actually build itself on fin unsafe. I just want the fins to be unsafe. I don't want the vex to be unsafe. I've done this sort of trick about safe and unsafe, right? You see, I've done this with all of my different structures. We're really only going to examine fin in the video, although you might have fun reading the code later to see all the other changes. Okay, so now here I have a problem because this f0 and fsuck not in scope. And that's because I've imported fin unsafe, and fin unsafe doesn't have f0 or fsuck. Yet I need those constructors, and I need them to have the same behavior as they used to in order for my vector implementation to be safe. So what I want to do now is I want to make pattern synonyms, of course. So I'm going to say pattern f0, and now I have to think about the type of f0. So for this, let's take a look at, I'm going to bring finsafe and put it over here. So f0 is fin of suck n. So what this means is that when I pattern match on f0, I'm going to learn that the index to fin is actually successor of something. And so my pattern here, what I really wanted to do is I wanted to be able to match on a fin n, no matter what I know about the n, but then I want it to produce information that that n is really the successor of some n prime. So for this, I need a bit of a fancy type signature that looks like this. I will explain it shortly. Okay, there it is. Now I think it will work better for me to get rid of this. Okay, so that's my type that I want to give to f0, the pattern synonym. And so what is this? This piece here, let's break this up into pieces. I should probably put the dots on the left, but I'm not going to bother doing that. That's boring. So here, these are the universal variables. These are the types that we need to know before we ever use f0. This would be the required constraints. To use f0, we don't require any particular constraints. These are existential variables. When the pattern match is successful, this is what we will bring into scope. So universals are needed before the pattern match. This is, I'll say, produced on successful pattern match. These are the provided constraints, also produced on successful pattern match. And then this is the scrutiny type. The type of the pattern that we're going to apply this pattern synonym to. This will have the same behavior that we have here for, oh, I don't want vecsafe, I want finsafe. Where's finsafe? Come back, finsafe. This is going to have the same behavior as this f0. GADT syntax allows us to compress all of this information, but really this is the same. My very fancy pattern synonym signature says the same thing as this GADT signature here. In a sense, this suck n, this n, is really a local variable n prime, and this is this sort of other, more universal n, and we have an equality relationship between them. Okay, so let's go back to fin unsafe. So I've written all of this out. Now, let me actually go ahead and try to define this. So this pattern f0 is going to be, well, we're going to have some function that identifies 0. So match f0 to, I don't know, true. We're going to come back to that in a minute. Okay, so now, why am I not getting all kinds of errors? Haskell language server, what are you doing to me? Why do you not check my module? I want you to check my module, and you are not doing it. If I change this back to use finsafe to make these errors go away, what happens? Ooh, nothing. It's just very confused. Okay, so we now have things working again, thankfully. I had to start and stop the Haskell language server a few times there. Okay, so let's see. Where are we? Now we can start to fix these errors. Yes, we would like some pattern synonyms. And here, oh, no code actions available. Well, I don't know what it's going to suggest. Might be rank n types if I try hard enough, but I know I want scoped type variables before too much longer. So let's just put that one in. Let's see down here, view patterns would indeed be nice. And then all of this gobbledygook. What is this gobbledygook? Oh yes, we'll need GADTs. Yes, good. And then now down here, what is this problem? Invalid right-hand side of bidirectional pattern synonym. Okay, so what this is saying is that my pattern f0 here, it says equals this view pattern. Well, a view pattern is very good for matching, but it's very bad for building, right? We don't know what it would mean for f0 to be in an expression with this. So the solution, as it suggests here quite nicely, is to do this. So it looks like there's maybe an opportunity for a code action there to just do that for me. Now, let's see, it is complaining, not in scope match f0, and then over here, could not match type n with suck n. We'll return to that second one in a bit. But the match f0 bit we can fix. So we want match f0, so this has to take in the fin n, the scrutiny, and it's going to return a bool. And match f0, if we see actually a 0, that's true, and then anything else is not so true. Okay, good. So that first error goes away, but then now we have over here, couldn't match type n with suck n prime 0. So what it's saying is that we don't know that n is the successor of anything at all. And that is coming from, it says, arising from the provided constraints claimed by the signature. What this is saying here is that on a successful pattern match of f0, we're going to learn that n, the type of the part of the type of the scrutiny, is in fact the successor of some other n prime. But even though I say that we can assume that, there's nothing about my pattern that actually does that. So this is not good enough. Instead, what we need is we actually need match f0 not to return a bool, but to return a GADT. So this is going to be the match f0 type. It's going to have the same index as the fin. And then if I write data match f0n, where mfz yes will tell us that this index is in fact the successor of some number, or mfz no won't tell us anything at all. It's just a match f0n. So here, this n is sort of my universal variable. This m is sort of my existential variable, and there's going to be a sort of an implicit equality relationship between them. Okay, so now that I have this match f0, this is now going to return match f0n. So we're going to learn more information about this index of the scrutiny. And now, of course, I need to write mfz yes and mfz no in these two cases. And then now, let's get rid of this thing, get rid of that thing. Now this is going to match mfz yes. And so everything down here is quite happy, but we've just sort of moved the problem around, right? Up here, we see that mfz yes, if I look at the error message, this is the same error message that we saw before, can't match n with suck of m0. And that's because here, for this, the use of this constructor to be valid, we need this match f0, we need this to be a suck n, but all we know is that it's an n. So what we have to do is we have to use unsafe features. this isn't really a surprise because we haven't encoded all of our type level invariants. Here, we're just matching on a normal number 0. And so we can't expect to sort of get anything for free. So what we do now is we're going to look at natunsafe, which is pre-cooked here to have this unsafe assume suck. So I think the details here I'm not going to go into in this video. But what we can see here is that for any n input, we're going to pass in a continuation. This is also a continuation passing style. In the continuation, we're going to learn that n is actually the successor of m, and it's doing this via unsafe coerce. So this is just a little bit of magic to whip up this proof that n is really the successor of something. That's exactly what we need here. So I can call unsafe assume suck, and what do I want to assume as a suck? I want to assume that this n is. Of course, n needs to be in scope, so we bring it into scope using scope type variables like this. Oh, and unsafe assume suck needs to be in scope, and probably a couple of other things. Oh, we need type applications, and we need to import natunsafe. Okay, look at this. We are green. Excellent. So this all actually works. So let's jump down here to vexsafe to see this working. And now it's saying not in scope data constructor F0. Aha. Well, we have to export it from this module. So here I'm just exporting fin, but I'm going to export F0 with fin. So this is a bit strange, right? Because F0 is a pattern synonym, and yet I've included it here as if it's a data constructor. So there's a feature in GHC allowing us to what's called bundle a pattern synonym in with a type constructor just for this use case. So now in vexsafe, when I import, where is it? When I import fin unsafe, I could actually include fin ... and I would get these bundled pattern synonyms. So here we go. That error is gone. Now we need to do it for fsuck. So we're going to just sort of repeat this game a little bit. I'm going to go a little faster this time. So if I do pattern fsuck, this is going to take in, for all n with no required constraints, and it's going to produce an n prime such that n is successor of n prime. And then fsuck, there's this sort of inner fin that we're going to get out of the match. So here we're going to get fin indexed by n prime, but my scrutiny is fin indexed by n. Let's see, what's the error that I'm getting? Oh, well, it lacks an accompanying binding. So we have pattern fsuck, and then this we have to play the same game all over again. So it's match fsuck, and this is going to be mfs. Yes. So now we're going to need our match fsuck with its kind signature and definition. And so we have mfs yes, and here this is going to carry fin m, and it's going to produce a match fsuck of suck m, and mfs no gives us nothing. Very boring. Looks like this. And now we need the match fsuck function that works much the same way as the last one. But here, in the body of the function, I'm going to check this is going to be unsafe mcfin n such that n is greater than 0. Right? This has to be the successor or something. So I still have to remember to do this, right? This module is all unsafe features, so I have to remember steps like this. The type system isn't going to remember for me. And so then here I can say that this is mfs yes, and I have to pass in the predecessor fin. So this is n minus 1. And otherwise, I can spell that correctly, is mfs no. It does not match. Okay. So all of these pieces, oh, it's still complaining about something. The result is mentioned existential. Oh, what have I done wrong? I haven't bound the F here. There we go. The reason that that particular error came up is that it was thinking that this whole thing was the scrutiny because it looked at the arity of the pattern and saw that the pattern took no argument. So it assumed that this whole thing was the scrutiny. Now that I've given it an argument, it realizes that this is an argument and this is a result. And as I believe we saw in a previous video, an existential can't be mentioned in a result. Okay, but now up here, we still have the same error because once again, we have to have unsafe assume suck at n Okay, are we green? Yes, we're green. Excellent. Now we go down here and, oh, not in scope. That's because we have to bundle it. So f0 and fsuck in the bundle. And now we go down to vexsafe. That bug is gone. But now here we have this f0, and the error is non-bidirectional pattern synonym f0 used in an expression. Why, yes, that's true. It really is that. And so here, now what we have to do is this f0, I want to be able to use this in an expression. So I want this to be, I can't make it a normal bidirectional pattern synonym. So we have to do what's called an explicitly bidirectional pattern synonym. It's quite a bit of a mouthful. So we say where f0, if used as an expression, well, that's quite easy. It's just unsafe McFin of 0. We're going to need the same treatment for fsuck. So we play the game again over here. So where fsuck of unsafe McFin, f is really unsafe, whoops, McFin of f plus 1. Because constructing these things is easy. It's really destructing them that's the problem. So now this has gone from red to yellow, and that's because here we get a pattern match is non-exhaustive. So if I go here, that's easy to fix. We just need a little complete pragma. Whoops, f0, fsuck. And now, aha, this is green. So let's see, what is vec unsafe complaining about? Unsafe int to fin size. Why is this complaining? Maybe my fin unsafe here. It's importing snat safe. We need to sort of line all of these things up. So if I import snat unsafe, then everything is lined up nicely. Okay, so let's go back to main here. We here, let's import vecsafe with fin unsafe. And now, I need nat. I guess I need nat safe in this case. Yes, because vecafin takes the safe snat. So this seems to compile. Let's actually build the thing. Churn, 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 churn. And in a moment, hopefully, we can run it. And now let's see its performance. Aha! So here we get 800,000 bytes. That's a bit less than the 1,000,000 bytes that we first saw. So this is using the safe vec, the linked list vec, but each element in the linked list is now just an int. It's not a separate linked list. So this uses fewer bytes of allocation. Hooray. So we saw a much better result earlier when we were actually using packed arrays. And that's because, as we see over here, I've done this for all of my rich data types. I have both safe and unsafe versions. And so we can sort of mix and match these. What's the upshot to all of this? The upshot is that by using these pattern synonyms and quite a bit of type level hackery, which is always fun, we can mock up we can create a safe interface around an unsafe implementation, right? So here, there's a lot of mistakes I could have made that my type system would not have caught, and that's why I need to use things like unsafe assume suck. But once I've done that, then a module like vecsafe can depend on fin unsafe and still have this nice pattern match here, and still use all of these fancy type level features in downstream modules, and allows us to sort of mix and match things as we go. I hope this has been interesting for you. Thanks very much for watching. Bye.